Imagine a world where yesterday, today, and tomorrow are not separate. Imagine being able to step into a machine and witness the rise and fall of civilizations or even meet your future self. Time travel may sound like science fiction, but physics tells us it might be closer than we think. Today we're going to explore the tantalizing possibilities of moving through time, guided by the science behind it, and what we know from the brilliant minds of theoretical physics. Time is one of the most mysterious and fascinating aspects of our universe. We often think of it as a simple, unyielding progression from past to present to future, measured by clocks and calendars. But physics teaches us that time is far more complex, far more flexible, and far more extraordinary than our everyday experience suggests. Imagine standing on a distant planet, orbiting a massive star where the pull of gravity is so intense that time itself slows down for you compared to someone back on Earth. A few years for you might mean decades for someone else. This is not science fiction. This is the reality of Einstein's theory of relativity. Time is a dimension, much like the three dimensions of space, intertwined with them in a fabric we call spacetime. The faster you move through space, the slower you move through time. This is called time dilation, and it has been experimentally confirmed countless times, from atomic clocks on jets to satellites orbiting Earth. Every time you fly across the globe, every time a satellite beams signal to your phone, you are participating in tiny acts of time travel. It is as if the universe is constantly offering us glimpses into the fluidity of time, showing that the past, present, and future are not as rigid as they seem. When we consider time as a malleable dimension, suddenly the idea of traveling through it does not sound absurd. It is as if time is a river, and relativity provides the currents and eddies that could allow us to drift forward or backward along its flow. Now, when we move from the concept of time as a flexible dimension to the tantalizing possibility of wormholes, the adventure truly begins. Wormholes, theoretically predicted by Einstein and Rosen, are bridges in the fabric of space-time. Imagine the universe as a two-dimensional sheet of paper. If you wanted to travel from one point to another, you could trace a straight line across the paper, but that might take a very long time. Instead, you could fold the paper so that the 2 points touch, and suddenly a shortcut opens between them. This is the essence of a wormhole, a tunnel connecting distant points in space and potentially in time. If a wormhole could be stabilized and traversed safely, it might allow a journey not just across galaxies, but across centuries. The mathematics of general relativity permits such structures, though creating one would require exotic matter, with negative energy density, something that is still hypothetical but not forbidden by the laws of physics. The very idea forces us to rethink our assumptions about the universe. Time is no longer a relentless river flowing in one direction. It becomes a navigable dimension, a path we might one day traverse. The implications are staggering. If wormholes exist naturally, as some cosmologists speculate, they could be the ultimate transportation networks, connecting different eras as easily as distant galaxies. And even if we cannot physically step into them today, understanding their properties illuminates the very nature of reality itself. The study of wormholes bridges theoretical physics and imagination, showing that the universe is not only stranger than we think, but stranger than we can think. The bending of space-time, the possibility of creating shortcuts across the cosmos, and the potential to glimpse the past or future all reside in the elegant equations of Einstein, inviting us to explore the frontier, where physics meets philosophy and science flirts with the realm of the impossible. The idea of time as a navigable dimension and the existence of wormholes also challenge our deepest intuitions about cause and effect. When we imagine stepping through a wormhole into the past, we must confront paradoxes that have perplexed scientists and philosophers for decades. The grandfather paradox, the possibility of altering history, and the questions of free will versus determinism become more than thought experiments. They become essential considerations in understanding how the universe operates on the most fundamental level. Physicists have proposed elegant solutions, such as the many worlds interpretation, where every action spawns an alternate timeline, allowing us to explore the past without erasing our existence. This is not merely speculation. Quantum mechanics has already shown us that particles can exist in multiple states at once, that observation affects outcomes, and that the boundaries of time and causality are not as rigid as classical intuition would suggest. Wormholes, in this sense, are not just tunnels through space, They are portals to profound questions about reality itself. They offer a laboratory for testing the limits of physics, imagination, and human understanding. Furthermore, the study of wormholes forces us to confront the role of energy and matter in shaping the universe. To keep a wormhole stable, theoretical physicists propose the use of negative energy, concept that challenges our everyday experiences and yet is permitted by the principles of quantum field theory. Casimir experiments have already demonstrated that negative energy can exist, albeit in tiny amounts. Scaling this up to a traversable wormhole remains a monumental challenge, but the fact that the laws of physics do not outright forbid it is extraordinary. It suggests that the universe is far more accommodating of the fantastical than we might have imagined. Time travel, once the exclusive domain of science fiction, becomes a serious topic of scientific inquiry. It forces us to expand our understanding, to explore realms where mathematics, quantum theory, and general relativity converge in ways that defy common sense yet remain firmly rooted in reality. The potential existence of wormholes also raises questions about communication and observation across time. Could we, in principle, send messages to the past or future without physically traveling? Some physicists speculate that advanced civilizations might already exploit such phenomena, leaving subtle imprints in cosmic radiation or gravitational waves. If wormholes are out there, hidden in the folds of space-time, they could fundamentally alter our understanding of causality and information. It is an exciting and humbling prospect, reminding us that the universe is far more complex and interconnected than our everyday lives reveal. The study of time and wormholes pushes humanity to think boldly, to imagine technologies and possibilities that challenge the limits of our current understanding. It is a celebration of curiosity, of the relentless drive to explore not just the physical universe, but the very nature of reality itself. Time, with its flexibility, and wormholes, with their potential as cosmic shortcuts, together paint a picture of a universe that is alive with possibility. They invite us to rethink what we consider impossible, to embrace the counterintuitive, and to explore the frontier where imagination meets rigorous scientific inquiry. They remind us that physics is not just about equations and experiments, it is about asking questions that expand our minds, open doors to discoveries that could transform our understanding of everything from the tiniest particle to the vast cosmos. By studying time and wormholes, we do not merely learn about the universe. We learn about the power of human curiosity, the capacity of the mind to envision realities far beyond immediate perception, and the exhilarating journey that awaits when science dares to dream. The elegance of relativity and the tantalizing possibilities of wormholes also force us to confront the limitations of our current technology and knowledge. While the equations permit these phenomena, engineering a practical method to navigate them is a challenge of unimaginable complexity. Yet this is precisely where the adventure lies. Science advances not merely by proving the possible, but by daring to explore the edge of what is conceivable. Every experiment, every theoretical breakthrough brings us closer to understanding whether the cosmic bridges are mere mathematical curiosities or tangible pathways through the universe. In contemplating wormholes, we confront questions about energy, matter, gravity, and the fabric of reality itself. Each of these is a doorway into deeper understanding, an invitation to explore the interplay between the laws of physics and the possibilities they allow. Even as we ponder the enormity of these concepts, one cannot help but be struck by the profound philosophical implications. If time is a dimension we might someday navigate, and if wormholes provide shortcuts across the cosmic expanse, what does that mean for our perception of life, destiny, and the universe? Are we mere passengers on a river of time? Or could we become navigators, charting courses across the ages? The study of these ideas, grounded in the rigor of physics, simultaneously liberates the imagination. It allows us to envision a future where humanity does not merely witness the cosmos, but interacts with it in ways previously relegated to the realm of fantasy. In exploring the nature of time and the potential of wormholes, we also encounter the beauty of mathematical consistency. The same equations that predict the behavior of stars, galaxies, and black holes also hint at the possibility of time travel. There is a sublime elegance in this unity, a reminder that the universe operates according to principles that are both precise and awe-inspiring. It is a call to curiosity, a challenge to explore, and an invitation to participate in the grand adventure of understanding reality at its deepest level. These ideas are not just theoretical exercises, they inspire real-world research, from particle accelerators to gravitational wave observatories. Each experiment, each observation brings us closer to understanding the universe's architecture and the potential pathways that may allow time travel to move from theory to practice. The pursuit itself, even if practical time machines remain distant, enriches our comprehension of physics, strengthens our technological capabilities, and expands our imagination. Time travel, as framed by the flexibility of time and the possibility of wormholes, becomes not just a scientific concept but a philosophical exploration. It challenges our notions of cause and effect, reality and perception, and the limits of human potential. By engaging deeply with these ideas, we participate in a tradition of inquiry that stretches back to the greatest thinkers in history: philosophers, mathematicians, and physicists who dare to imagine worlds beyond immediate experience. It is in this intersection of imagination, mathematics, and observation that the true excitement of time travel lies. It teaches us that the universe is not a static backdrop, but a dynamic, evolving tapestry of possibility. Each step in understanding time and wormholes opens new questions, new avenues of research, and new horizons for exploration. In contemplating these ideas, we are reminded that science is ultimately an adventure of the mind, a journey that transforms not just our knowledge, but our very sense of what it means to exist in the cosmos. The interplay of time as a flexible dimension and wormholes as potential bridges invites us to reconsider the limitations of our perception and technology. It encourages bold thinking, daring experimentation, and relentless curiosity. It suggests that the boundaries between science fiction and science fact are not as rigid as we once believed. As we continue to explore these ideas, we deepen our understanding of the universe, challenge our assumptions, and ignite the imagination in ways that inspire generations of scientists, thinkers, and dreamers. Time and wormholes remind us that reality is far more wondrous than the familiar world of clocks, calendars, and ordinary experiences. They open our minds to the extraordinary, showing that the universe is rich with possibilities waiting to be discovered. They teach us patience, humility, and wonder, qualities essential for anyone seeking to comprehend the cosmos. By studying these phenomena, we engage in a dialogue with the universe itself, asking questions that may ultimately redefine our understanding of existence, causality, and the very nature of reality. The very idea of time travel forces us to confront paradoxes that stretch the imagination and challenge the deepest intuitions about reality. Among the most famous is the grandfather paradox, which asks, what happens if a time traveler goes back and prevents their own existence by altering past events? At first glance, it seems impossible, a logical contradiction that undermines the very notion of temporal travel. Yet physics suggests possible resolutions that are both elegant and profoundly intriguing. One of the most compelling ideas comes from quantum mechanics and the concept of parallel universes. In this framework, every action creates a branching of reality into a new, separate timeline. If a traveler were to intervene in the past, they would not erase their original existence. Instead, they would enter an alternate timeline where different events unfold. The original timeline remains untouched, preserving causality in a way that reconciles the seeming contradictions. This is not merely science fiction speculation, it is a logical extrapolation of the principles of quantum mechanics, where particles can exist in multiple states simultaneously and outcomes are probabilistic rather than deterministic. The notion of multiple timelines expands our understanding of cause and effect, suggesting that reality is not a single rigid thread, but a vast, branching network of possibilities, each as real as the one we perceive. When we move from the macroscopic paradoxes of time travel to the microscopic world, quantum mechanics offers even more fascinating insights. At the quantum level, particles do not behave in ways that align with our everyday experience of time. Experiments reveal that particles can be entangled, influencing each other instantaneously over vast distances, and in some cases, the effects seem to propagate backward in time. This does not violate causality in the conventional sense, but it hints at a universe where the flow of time is far more flexible than our linear experience suggests. The quantum world, in which uncertainty and superposition reign, provides a laboratory for testing the limits of time. It suggests that our intuitive notions of past, present, and future may be emergent properties rather than fundamental truths. In this sense, time travel at the quantum level is not only conceivable, but may already occur in subtle ways, woven into the very fabric of reality. These phenomena challenge our understanding of cause and effect and invite us to consider that time is not a one-way street, but a multi-dimensional landscape that can be navigated in ways previously unimaginable. The interplay between time travel paradoxes and quantum mechanics raises profound philosophical and scientific questions. If each choice generates a new timeline, then every decision we make is a step into countless potential realities, each branching from the other in an infinite cascade. The implications for free will, destiny, and personal responsibility are staggering. In a multiverse scenario, the consequences of our actions are both constrained and liberated, constrained in the sense that each timeline has its internal logic, but liberated because our choices do not irrevocably limit the universe. The universe, in this view, is a vast, interconnected web of possibilities, and time travel becomes not just a journey through chronological intervals, but a navigation of potential realities. This perspective transforms the concept of time travel from a fantastical curiosity into a profound exploration of the nature of existence itself, linking physics, philosophy, and metaphysics in a remarkable synthesis. Another avenue of inquiry into time travel lies in the behavior of particles at the quantum scale. Quantum entanglement, the phenomenon where particles remain interconnected regardless of distance, demonstrates that the universe is far more interconnected than classical physics suggests. When one particle is manipulated, its entangled partner responds instantaneously, regardless of spatial separation. This spooky action at a distance, as Einstein famously described it, challenges our classical understanding of space and time. Furthermore, experiments in which particles appear to influence their past states provide tantalizing hints that time, at least on a microscopic scale, is not strictly linear. While these effects are subtle and confined to the quantum realm, they open the door to revolutionary ways of thinking about time travel. If the rules that govern the quantum world can be harnessed or understood in new ways, the dream of traveling through time may not be entirely beyond the reach of physics. The study of these quantum effects also intersects with theoretical work on wormholes and space-time curvature. In some advanced theories of quantum gravity, space-time is not smooth, but fluctuates at extremely small scales, creating a frothy, dynamic environment where microscopic wormholes could form spontaneously. These tiny bridges, while not yet accessible to macroscopic objects or humans, provide a theoretical mechanism by which time and space might be interconnected in unexpected ways. The universe, in this view, is alive with hidden structures that, if properly understood, could allow information or even matter to traverse time in ways that challenge conventional experience. The synergy between quantum mechanics and general relativity, law considered incompatible, becomes a fertile ground for exploring the physics of time travel, showing that even the most counterintuitive concepts can emerge naturally from the laws that govern reality. Exploring time travel paradoxes and quantum phenomena also reshapes our understanding of causality. In classical physics, every effect has a cause, and time moves inexorably forward. But quantum mechanics and multiverse interpretations suggest a more nuanced picture where cause and effect are probabilistic and branching rather than deterministic and linear. In this framework, time travel does not necessarily disrupt the universe. Instead, it adds layers of complexity to a cosmos that is already rich with possibilities. This insight transforms time travel from a mere fantasy into a scientifically grounded concept, inviting serious inquiry into its mechanisms and implications. It challenges us to rethink what is possible and encourages a perspective in which the universe is far more malleable and interconnected than our intuition suggests. Moreover, the exploration of time travel at both macroscopic and quantum levels has practical implications for future technology and scientific research. Understanding how time can bend, loop, or branch could inform advanced communication methods, high-energy physics experiments, and perhaps even novel ways of storing and transmitting information across temporal intervals. The study of paradoxes, far from being purely theoretical, drives innovation in understanding the structure of space-time, the behavior of particles, and the fundamental limits of physical laws. In grappling with these concepts, Scientists are not merely indulging curiosity. They are laying the groundwork for technologies that may one day allow us to interact with time in ways that are now unimaginable. The philosophical implications of these phenomena are equally profound. If multiple timelines exist, then the universe is not a single immutable story, but a vast anthology of interconnected narratives, each as real as the other. Our choices, actions, and experiments ripple through these narratives, influencing outcomes in ways that challenge conventional notions of responsibility and causation. Time travel, paradoxes, and quantum mechanics together create a vision of reality that is not linear, not deterministic, but fluid, dynamic, and brimming with possibility. It suggests that the universe is not merely a backdrop for our existence, but a participatory arena where observation, choice, and understanding shape the unfolding of events across both space and time. By studying these paradoxes and quantum effects, we also gain insight into the ultimate nature of information and the limits of knowledge. If time can branch, loop, or be influenced by quantum events, then the universe contains layers of information that are both hidden and accessible, waiting for advanced civilizations or sophisticated technologies to decode. Each discovery brings us closer to understanding the deep structure of reality, revealing the universe as a rich tapestry of interwoven possibilities. Time travel, once dismissed as fantasy, becomes a lens through which we can explore the deepest questions about existence, causality, and the cosmos itself. The connection between time travel paradoxes and quantum mechanics also underscores the importance of imagination in scientific inquiry. Some of the greatest breakthroughs in physics have begun with thought experiments, mental exercises in which scientists asked, what if? By imagining the consequences of traveling to the past or exploring multiple timelines, physicists are not merely indulging speculation, they are probing the logical structure of the universe, testing the boundaries of known laws, and expanding the domain of what is scientifically conceivable. Time travel, in this sense, becomes a tool for understanding reality itself, pushing the mind to consider possibilities that lie far beyond everyday experience. As we contemplate the paradoxes and quantum behavior underlying time travel, it is important to recognize that these are not isolated curiosities. They are interconnected with some of the deepest questions in physics, the unification of general relativity and quantum mechanics, the nature of space-time at the smallest scales, and the limits of information transfer. Each insight into these phenomena not only illuminates the possibility of moving through time, but also enhances our understanding of the universe as a coherent, intelligible, and astonishingly complex system. In this interplay of paradox and quantum strangeness, we see the frontier of knowledge expanding, a frontier where imagination, mathematics, and empirical science converge to reveal the extraordinary character of reality. Time travel, when examined through the lens of paradoxes and quantum mechanics, invites a profound reconsideration of reality itself. It challenges our notions of linearity, causality, and determinism, and it opens the door to a universe in which multiple outcomes, branching timelines, and subtle influences across time are not only possible, but intrinsic to the fabric of existence. These ideas, while daunting, are also exhilarating, offering a glimpse into a cosmos that is richer, more dynamic, and more mysterious than our everyday perceptions reveal. By exploring these concepts, we engage with the universe at its most fundamental level, embracing the complexity, wonder, and limitless potential that time, space, and quantum mechanics offer to those who dare to inquire deeply. Black holes, often thought of as mere cosmic vacuum cleaners, are in fact some of the most intriguing laboratories for the study of time itself. Near a black hole, gravity is so intense that it warps space-time to an extraordinary degree, causing time to slow dramatically relative to distant observers. This phenomenon, predicted by Einstein's theory of general relativity, has been confirmed through numerous observations, including the precise timing of pulsars orbiting dense stellar remnants. Imagine orbiting a massive black hole safely in a spacecraft. Years might pass for you while decades unfold for those far away. This is not speculation. It is a direct consequence of the equations governing the universe. The implications are profound. A black hole could, in principle, act as a natural time machine, allowing travelers to experience the future at a rate far faster than those who remain distant from such intense gravitational fields. The universe, it seems, offers its own pathways through time, not through machines or science fiction constructs, but through the extraordinary curvature of space-time itself. This realization forces us to reconsider what we mean by the flow of time. Time is no longer uniform, it is malleable, influenced by mass, velocity, and the geometry of the cosmos. The very fabric of reality is alive with gradients of temporal experience, and by understanding these gradients, we glimpse the possibilities of navigating time itself. Black holes also present a unique interface between general relativity and quantum mechanics. As matter approaches the event horizon, the boundary beyond which nothing can escape, the gravitational distortion of time becomes extreme, while quantum effects become increasingly significant. The merging of these domains hints at a deeper understanding of space-time, one that could potentially inform future attempts at controlled time travel. The concept of Hawking radiation, whereby black holes emit energy due to quantum effects near the horizon, suggests that even these seemingly inscrutable cosmic objects are governed by a delicate balance of physical laws, providing tantalizing clues about the interplay between gravity, time, and the quantum world. In contemplating black holes as natural time machines, we recognize that the universe itself is offering a template for understanding temporal manipulation, highlighting pathways that, while extreme and currently inaccessible, illustrate the profound connection between time and the structure of space-time. Practical obstacles remain immense. To harness a black hole as a conduit through time, one would need to withstand phenomenal tidal forces, protect against lethal radiation, and navigate an environment where conventional physics is pushed to its extremes. Even traveling close to the speed of light presents challenges of unimaginable complexity. The energy requirements alone are staggering, yet these constraints do not negate the possibility. They merely frame it within the realm of advanced engineering and future technological breakthroughs. The history of science shows that what seems impossible today may become routine tomorrow as our understanding deepens and our technological prowess grows. The obstacles are part of the adventure, part of the intellectual journey that drives humanity to test the limits of what is possible and to explore realms once thought to belong exclusively to imagination. It is this interplay between theoretical possibility and practical limitation that makes the study of black holes and time travel so compelling. Beyond black holes, wormholes offer another tantalizing avenue for navigating time. To stabilize a wormhole, theoretical physicists propose the use of exotic matter with negative energy density. This exotic matter, while not yet observed in quantities sufficient for macroscopic structures, is permitted by the laws of quantum mechanics. The Casimir effect, a phenomenon observed in laboratory experiments, demonstrates that negative energy can exist in principle, creating a repulsive force between closely spaced metal plates. Scaling this effect up to stabilize a traversable wormhole is a monumental challenge, yet it is a challenge grounded in the mathematics of the universe rather than the imagination of writers. Wormholes, if they can be realized, would provide direct shortcuts not only across space, but potentially across time, linking epochs in ways that defy ordinary perception. These hypothetical structures illuminate the possibilities inherent in the curvature of space-time, showing that the universe, through the language of Einstein's equations, permits routes that are both extraordinary and theoretically sound. Exploring the theoretical requirements for time travel via wormholes also forces us to confront fundamental questions about the nature of energy, stability, and causality. Negative energy, while exotic, is not forbidden. It is a resource that could, in principle, be harnessed to bend space-time. The manipulation of such energy could allow the creation of regions where time loops back upon itself, enabling journeys to the past or future. The equations of general relativity, far from forbidding these constructs, suggest that they are consistent with the known laws of physics, highlighting a profound truth. The universe is more accommodating of the fantastical than common intuition would allow. Wormholes are more than theoretical curiosities. They are windows into the deep structure of space-time, revealing the latent possibilities of temporal navigation and the subtle interplay between matter, energy, and geometry. The study of these extreme scenarios, black holes, near light speed travel, and wormholes, also underscores the intimate relationship between time gravity, and energy. Each insight deepens our appreciation of the universe's complexity and challenges our preconceptions about what is possible. As we probe the edges of physics, we begin to see that time travel is not a whimsical idea but a serious scientific question constrained by the laws of nature but permitted by them in surprising and elegant ways. This perspective shifts the discussion from fantasy to frontier science, showing that the concept that once seemed purely fictional now reside within the domain of legitimate inquiry. The universe is a vast, dynamic system, and by studying its extreme environments we learn not only about time travel, but about the fundamental architecture of reality itself. In contemplating black holes and wormholes, we also confront the role of observation and technology in shaping our understanding. The detection of gravitational waves, the imaging of black hole shadows, and precise astronomical measurements provide empirical access to regions of space-time where the warping of time is extreme. These observations allow us to test predictions, refine theories, and explore the possibility of time travel in a manner grounded in empirical science. Each breakthrough illuminates the path toward understanding how the universe permits extraordinary phenomena, highlighting the delicate balance between theory, observation, and imagination. The philosophical implications of these ideas are profound. If black holes can act as natural time machines, and if wormholes could potentially be stabilized to connect distant points in space-time, then our intuitive understanding of causality and temporal progression must be re-examined. Time is no longer an inexorable uniform flow, it is a flexible navigable dimension subject to the influence of mass, energy, and geometry. These revelations challenge our perception of the universe, inviting us to consider that the future may be as accessible as the past, that reality is not fixed but dynamic, and that the cosmos itself is far richer and stranger than everyday experience suggests. The study of black holes and wormholes also inspires innovation in other areas of physics. Concepts developed in these contexts influence research in quantum gravity, high-energy physics, and cosmology. They stimulate new experiments, new technologies, and new ways of thinking about energy, space-time, and information. Even if practical time machines remain beyond our current capabilities, the intellectual journey opens doors to understanding phenomena that were previously inconceivable, fostering a deeper connection to the universe and a broader perspective on the possibilities that physics allows. Exploring these extreme environments highlights the interplay between imagination, theory, and observation. The equations of general relativity provide the framework, quantum mechanics introduce subtle possibilities, and empirical observation tests the limits of our understanding. In this synergy, time travel emerges not as a fantasy but as a profound scientific question, demanding both creativity and rigor. It illustrates the extraordinary power of the human mind to grasp concepts that are far removed from everyday experience and to probe the deep structure of reality itself. Finally, considering black holes and wormholes as mechanisms for time travel reminds us of the vast potential of the universe and the opportunities for discovery that lie ahead. Each theoretical breakthrough, each technological advance, and each observational insight brings us closer to understanding how time can be navigated, stretched, or even manipulated. The universe is not a static backdrop, but an active, dynamic system full of possibilities waiting to be explored. By studying the extreme curvature of space-time, the behavior of energy and matter, and the theoretical constructs of wormholes, we glimpse a reality that is profoundly more flexible and wondrous than everyday perception suggests. The investigation of these phenomena is a testament to human curiosity, pursuit of knowledge, and the capacity of science to transform the seemingly impossible into a field of serious inquiry, opening the door to discovery that may one day allow us to traverse the very fabric of time itself. As we look to the future of time travel research, we are compelled to confront the extraordinary frontiers where physics, imagination, and technology converge. Scientists are exploring avenues that stretch the limits of our current understanding, from the behavior of cosmic strings, hypothetical defects in space-time left over from the early universe, to advance experiments in quantum gravity and high-energy particle physics. Cosmic strings, if they exist, could warp space-time to such a degree that they might permit shortcuts through time, acting as natural conduits connecting different epochs. These hypothetical filaments, thinner than an atom yet incredibly dense, possess gravitational effects so extreme that, in theory, moving along or near them could allow a traveler to leap forward or backward in time. While this remains speculative, The mathematics describing such phenomena is robust, showing that the universe is rich with possibilities that may someday move from theoretical constructs to testable hypotheses. Each step in this research deepens our comprehension of the universe, revealing subtle structures and hidden mechanisms that challenge conventional notions of causality and the linear progression of time. Quantum gravity, the effort to reconcile general relativity with quantum mechanics, also offers tantalizing insights into the future of time travel. At the Planck scale, space-time is thought to be granular, fluctuating in a frothy, chaotic manner. These minute distortions could, in principle, host transient wormholes or micro-bridges through time. While we cannot yet manipulate these directly, understanding their dynamics illuminates the very nature of time itself. It suggests that time is not a smooth, continuous river, but a complex, dynamic landscape, woven with microscopic structures that encode the potential for extraordinary phenomena. Research in this domain pushes the boundaries of both mathematics and technology, inspiring new ways to conceptualize the universe and test the limits of what is physically possible. The pursuit of these questions exemplifies the interplay between theoretical physics and the aspirational drive of human curiosity. It reminds us that even the most extreme ideas, once relegated to the realm of fiction, can become legitimate topics of scientific investigation when approached with rigor, creativity, and imagination. Equally compelling are the broader philosophical and practical implications of advancing time travel research. If humanity ever discovers a method to navigate time, even in the most limited sense, it would revolutionize our understanding of history, causality, and our place in the cosmos. The possibility of observing future civilizations, studying the evolution of galaxies, or even communicating across centuries challenges the very notions of experience, memory, and identity. Time travel research forces us to grapple with questions about responsibility, the ethics of intervention, and the nature of knowledge itself. Every hypothesis tested, every simulation conducted, and every experiment performed in this field extends our grasp of reality, showing that time is not merely a backdrop to existence, but a dimension ripe for exploration and understanding. Beyond theoretical exploration, these studies have profound implications for technology. If the principles underlying cosmic strings, wormholes, or quantum temporal effects can be harnessed, they may one day inform the creation of devices capable of manipulating time on a local or controlled scale. Even modest advances, such as the precise synchronization of atomic clocks in varying gravitational fields or the transmission of information through entangled quantum systems, offer glimpses of a future where time can be measured, influenced, and perhaps traversed in ways currently unimaginable. These technologies, while nascent, demonstrate the tangible potential of research into the structure of space-time, highlighting that scientific progress often begins with audacious ideas that stretch beyond immediate practicality. The study of time travel is also a celebration of human creativity and intellect. It invites scientists to explore questions that were once considered beyond reach, to construct mathematical frameworks for phenomena that challenge intuition, and to imagine technologies that may redefine the human experience. Each theoretical advance, each new model, and each experimental result contributes to a growing understanding of the universe, showing that the frontiers of knowledge are limited only by the boundaries of curiosity and imagination. By embracing the challenge of understanding time, researchers honor a tradition that spans centuries, from the early philosophers pondering the nature of causality to modern physicists probing the deepest structures of reality. When considering the significance of time travel, it is essential to recognize its role in shaping our understanding of the universe. Time travel is not an isolated curiosity. It is intimately connected to the most fundamental questions in physics. How does gravity interact with quantum fields? What is the ultimate structure of space-time at its smallest scales? How do information and causality behave under extreme conditions? By investigating these questions, scientists are not merely seeking fantastic adventures, they are exploring the architecture of reality itself. The pursuit of time travel is, in essence, a pursuit of knowledge, a quest to comprehend the rules that govern the cosmos, and to unlock the potential of phenomena that until recently were considered beyond reach. The implications of this research extend even further, suggesting new ways to think about civilization, technology, and our trajectory as a species. If humanity were able to observe the future or access distant epochs, our approach to innovation, problem solving, and long-term planning could be transformed. Understanding the malleability of time might provide insights into sustainable development, space colonization, and the management of cosmic scale challenges. In this sense, time travel is not only a theoretical adventure, but a lens through which we can envision a more advanced, interconnected, and conscious civilization. Furthermore, the pursuit of understanding time travel exemplifies the power of interdisciplinary research. It brings together general relativity, quantum mechanics, high-energy physics, cosmology, and even information theory, creating a rich tapestry of inquiry where each domain informs the other. Progress in one area often sparks insights in another, demonstrating that the universe is a coherent, interconnected system in which the laws of physics manifest in surprising and elegant ways. The integration of diverse fields of study is essential to uncovering the full potential of time travel, highlighting the collaborative and cumulative nature of scientific exploration. The study of time travel also illuminates the relationship between the possible and the practical. While current technology cannot yet manipulate black holes, stabilize wormholes, or traverse cosmic strings, understanding the theoretical constraints and possibilities guides experimental design, inspires innovation, and forms future technological development. It emphasizes that the pursuit of knowledge is not limited by immediate feasibility, rather, it is driven by the boldness to imagine, the rigor to analyze, and the creativity to explore scenarios that push the boundaries of what is considered achievable. Each insight gained, no matter how abstract, enriches our understanding of the universe and prepares the foundation for future breakthroughs that may one day make the fantastical tangible. As research advances, the exploration of time travel will continue to challenge our perceptions of reality, encouraging us to question deeply held assumptions about the nature of causality, temporality, and existence itself. It teaches us that the universe is not a static stage, but a dynamic, malleable, and profoundly interconnected system in which time itself can be influenced by mass, energy, and geometry. By engaging with these concepts, we cultivate a mindset that is both rigorous and imaginative, capable of grappling with the most complex and counterintuitive phenomena that the cosmos has to offer. In contemplating the future of time travel research, we also recognize the inspirational power of such inquiry. These studies capture the imagination, ignite curiosity, and motivate generations of scientists, engineers, and thinkers to push the limits of understanding. Time travel becomes not only a scientific question, but a symbol of humanity's drive to explore, to innovate, and to reach beyond the confines of immediate experience. It exemplifies the interplay between theory and imagination, showing that even the most audacious concepts can guide real-world research and technological advancement. Finally, the pursuit of time travel encourages a profound humility and awe in the face of the cosmos. The universe, with its black holes, wormholes, cosmic strings, and quantum complexity, is far more intricate and wondrous than everyday perception suggests. By studying these extreme phenomena, we engage directly with the underlying principles that govern existence, gaining insights not only into time and space, but into the very nature of reality itself. The endeavor to understand and eventually navigate time is a testament to human curiosity, intellect, and imagination, illustrating the remarkable capacity of science to transform the impossible into the conceivable, the fantastical into the investigable, and the distant future into a domain of inquiry rich with potential and discovery. As we step back from these mind-bending concepts, the warping of time near black holes, the tantalizing possibilities of wormholes, the paradoxes of altering the past, and the strange behaviors of the quantum world, we begin to see a universe far richer and more dynamic than our everyday experience suggests. Time is not simply a river flowing in one direction. It is a dimension we may one day navigate, a landscape shaped by gravity, energy, and the deepest laws of physics. The pursuit of understanding time travel is more than a quest for adventure. It is a journey into the very fabric of reality, challenging our assumptions, expanding our imagination, and inspiring us to reach for discoveries that can transform how we see ourselves and the cosmos. Whether these possibilities become reality in our lifetimes or centuries from now, the act of exploring them reminds us of the extraordinary power of human curiosity, creativity, and intellect. Thank you for joining this journey through the mysteries of time. Your curiosity fuels the exploration of these incredible concepts, and together we continue to dream, learn, and push the boundaries of what is possible. Keep wondering, keep imagining, and remember, the universe is far more wondrous than we can ever fully comprehend, and our adventure into understanding it has only just begun. Thank you so much for watching.